Welcome back. This is our second installment talking about quasi-Newton methods. And in particular, we're going to talk about perhaps the most widely used quasi-Newton method, called by the first letters of the names of the people that invented it, BFGS. So this is named after Broyden, Fletcher, Goldfarb, and Shano. So remember, what are we trying to do here? We have gradient descent, which is xt. Let's write this down again. Gradient descent, which tells us that xt plus 1 equals xt minus eta times the identity times the gradient of f of xt. And on the other extreme, we have Newton's method, which says that xt plus 1 is equal to xt minus eta times the Hessian inverse times the gradient. And we want to see, what's in the middle here. Newton's method is much more expensive per iteration. Gradient descent is much less expensive, but also much slower, even in the best setting. So our key goal is to replace this identity with something that looks a little bit more like this inverse Hessian, but we don't want to pay the price of that expensive computation of computing and inverting the Hessian. The key idea behind BFGS, and indeed an entire family of quasi-Newton methods, is to build this approximation recursively, and to build it by taking advantage of the trajectory that's mapped out by the algorithm. So the algorithm itself is visiting several points in the landscape, and that can potentially tell us something about the curvature. And the curvature is exactly what the Hessian matrix encodes. So we're going to talk about the specific BFGS way of achieving this. There are many methods here, and even for BFGS, there's a number of details that we're not going to have time to delve into. So I wanted to mention that an excellent reference for all of this is the book called Numerical Optimization by Nasadal and Wright. A starting point, just like our starting point for Newton's method, which was that we minimize the best, or the Taylor, second-order Taylor series approximation of our function. A starting point for any quasi-Newton method is just a simple observation that any quadratic approximation, not necessarily just the Taylor series, is gives us a good direction. So in other words, if I write down f, let's switch back to our main color, f of xk, I'm going to do a second order, I'm going to approximate f around the point xk with some second order approximation. So I'm going to call the second order approximation m sub k, to remind us that it's built around x of k. And I'm going to just indicate that it's a function of d because indeed I'm just trying to approximate it around x of k, so different directions. xk is fixed, d is a variable. And a generic second order approximation of f might look like f of xk plus the gradient of f of xk dot product with d. This is a linear approximation. Plus 1/2 times d transpose times something else here. So something that is going to approximate my Hessian. Again, if I plug in d equals 0, I get xk. So this is a perfect approximation at the point xk, and it's a quadratic approximation for non-zero d. So the point is that given this approximation, I can just minimize the right-hand side and find that dk is equal to minus bk inverse times the gradient of f of xk. That's the optimal dk. Again, we've done this kind of operation many times. I just looked at the right-hand side. That's a convex quadratic. I can just take the derivative, set it equal to 0, and therefore find that its minimizer is this d. So that's saying that if indeed your function were equal to the right-hand side, then the best next step to take would be xk plus d, or plus some multiple of d, which is equal to this. So our quasi-Newton method, derived by this starting point, any quasi-Newton method would say that xk plus 1 is equal to xk minus eta times bk inverse times the gradient of f of xk. I'm going to allow my step size to depend on the iteration. So the step size is typically chosen by backtracking line search, which we discussed in the context of Newton's method. We're going to go into more detail on exactly what flavor of backtracking line search we need in a few slides. But for now, it's enough to mention that this is chosen by backtracking line search. And I'll specify the details later. So you see that I've also put a subscript k on B. So what this allows is, and the key idea behind what we're going to talk about, BFGS, is that we want to update BK iteratively. And so this could potentially allow me to have a very rich BK, but without having at every single step to recompute a BK from scratch, and therefore fill in n squared new numbers. And ideally, we want something that where taking the inverse is not going to be too expensive. So we want to update BK iteratively, and there's two objectives, or two desiderata that we might have. So first, and very natural, is that we would like to do this so that we would like the key operation, namely the computation of dk. So we would like bk inverse times the gradient of f of xk to be easy to compute. I put easy in quotes. All that really means is easier than Newton. Because if it's not easier than Newton, I'm just going to use Newton's method. Easy to compute. And then I would like bk to be some reasonable approximation of the Hessian. And answering bk is basically going to specify what flavor of quasi-Newton method are we going to take. So what would we like? The key idea in BFGS is to have this quadratic approximation at time k. We would want mkd to capture curvature information of f along the trajectory that we've seen. So let's see exactly what this means. So I want to revisit B a little bit more carefully. So what should condition B capture? The BFGS idea, the core behind BFGS, is that we would like, so we know that what is mk and mk plus 1 and so on. We know that f of xk plus d is approximately equal to mk of d. And at the next iteration, we also hope that f of xk plus 1 plus d to be approximately equal to mk plus 1 of d. So what we would, the way that we're going to try to match curvature along the trajectory is to explicitly ask that mk plus 1 actually matches the slope at 2 points. If you match the slope, meaning you have the same slope as f, exactly at 2 points. So if you match the slope at 2 points, that again is like capturing some amount of curvature information. So the idea is, let's require, we're going to try to design BK so that, or BK plus 1, we're going to require that MK, and then therefore MK plus 1, matches the gradient of f, evaluated, not everywhere, then the only choice would be to have it be exactly the Hessian, but to match the gradient of f at the last 2 iterations. So I would like the gradient of mk plus 1 to give me the gradient of f of x at k plus 1, and also the gradient of f evaluated at xk. So let's see what that is. So if, looking at this top line here, f of xk plus 1 plus d is approximately equal to mk plus d, that means that I want, so the first point is that I want the gradient of mk plus 1 evaluated at d equals 0. So d equals 0 means that I should have this equal to the gradient of f at xk plus 1. This should equal the gradient of f of x k plus 1. And then I also want the gradient of mk plus 1 to match the gradient of f at xk. So what is xk? And how am I going to get that from f? What is xk compared to xk plus 1? And so in other words, mk plus 1 evaluated at 0 is like evaluating f at xk plus 1. How do I evaluate mk plus 1 effectively at xk? Well, I just evaluate, I use exactly what my update is. My update, I'm going to evaluate this at minus eta k dk. And I'm going to require that this is equal to the gradient of f of xk. Again, what I used here is that xk plus 1 is equal to xk plus eta k dk. Remember, dk already has a minus sign in it. And therefore, this is just equivalent to writing xk is equal to xk plus 1 minus eta k dk. So if mk plus 1, looking up here, if mk plus 1 evaluated at d wants to approximate f of xk plus 1 plus d, then if I evaluate mk plus 1 at minus eta k dk, that wants to be like f of xk plus 1 minus eta k dk, which should be like f of xk. Okay, so this is where this comes from. This is where this comes from. Okay, so this is kind of the key idea of BFGS. So let's look at what these two equations imply, what these two requirements imply. So we've got, again, writing out what mk plus 1 is. Mk plus 1 of d is equal to f of xk plus 1 plus the gradient of f of xk plus 1 transpose d plus 1/2 d transpose b k plus 1 d. So the two conditions I just mentioned are going to impose something on bk plus 1. What is the gradient of mk plus 1 at a generic d, at a general d? This is equal to, first term is 0 because I'm taking the derivative with respect to d. Second term is linear in d, so the gradient with respect to d just leaves gradient of f of xk plus 1. And then the final term, I just extract the linear term by taking the derivative. So the gradient is equal to this. Okay, so writing again our two conditions from the previous slide, we needed the gradient of mk plus 1 of 0 to equal the gradient of f of xk plus 1. What does this impose on bk plus 1? Well, looking, I see that if I plug in d equals 0 for the gradient, Actually, this is already satisfied, so we're all set. So this is automatically satisfied for any choice of bk plus 1. Okay, let's look at the second condition. The second condition requires that the gradient of mk plus 1 evaluated at minus eta k dk to equal the gradient of fxk plus 1. So what is the gradient of mk plus 1 minus eta k dk? Just writing it out, this is equal to the gradient of f of xk plus 1 minus eta k bk plus 1 dk. I just plugged in for d minus eta k dk. That's how I got this. And we want this to equal the gradient of f of xk. Okay, so now we have a non-trivial requirement for bk plus 1 to satisfy. So this is good. We're looking for, we started from a principle. Let's have our quadratic approximation match curvature in the sense that it matches the curvature from the past two iterations, the slope from the past two iterations. And we see that this imposes conditions on bk plus 1. In other words, it gives us guidance as to what bk plus 1 should satisfy. What should it look like? Now let's write what those say. And so here is my condition that I have on bk. So writing that out, this basically says that eta k bk plus 1 times dk is equal to the gradient of f of xk plus 1 minus the gradient of f of xk. I moved this term to the right and moved this term over to the left. Now, writing out what eta k dk is, so again, recall that xk plus 1 is equal to xk plus eta k dk. Don't forget that. Don't be confused by this plus here. dk already has a built-in minus sign if you look at its definition. So again, the simple relationship that eta k dk is equal to xk plus 1 minus xk. So therefore, this condition is exactly bk plus 1 times xk plus 1 minus xk has to equal the gradient of f of xk plus 1 minus the gradient of f of xk. This is a fundamental part of what defines BFGS, and sticking to notation that is common in the literature and definitely common in the book I cited, writing this as sk. So again, sk is just the difference between xk plus 1 and xk, and writing this as yk is the difference between the gradients, we have what's known as the secant equation, which is just what's written above. bk plus 1 sk is equal to yk. So bk plus 1 has to satisfy this. So now let's see how this is going to help us to define a good choice of bk. bk is an n by n matrix. There are order n squared degrees of freedom. I say order because it has to be symmetric. So just giving that one secant equation is not uniquely going to define bk. So the way that we can define bk is also asking for bk plus 1 to be close to the previous bk. So again, this is sensible. It's especially sensible if we're hoping to come up with an algorithm that iteratively and therefore in a less expensive manner updates from bk minus 1 to bk, from bk to bk plus 1, and so on. So what we're going to ask for is bk plus 1. I want this to be symmetric. So I'm going to define this as an optimization problem, but I'm going to ask that it's symmetric. and I'm going to ask that it is satisfying the secant equation, BSK equals YK. Okay, and as I said, this still leaves many degrees of freedom, and I'm going to resolve all of those just by using optimization. So BK plus 1 will be the argmin of B minus BK subject to these constraints. So this is basically just saying, what's BK plus 1? Please find something as close as possible to the previous iterate, BK. Again, this is natural. If you think about Newton, our analysis in Newton in the previous sequence of lectures, the key requirement was that the Hessian is Lipschitz. That means that if you evaluate at nearby points, the Hessian doesn't change too much. And BK and BK plus 1 are trying to evaluate an approximation to the Hessian at subsequent points of the iteration. So it's natural to ask that they don't change too much. So this is saying, find BK plus 1 that's close to BK, is of course symmetric because it has to be symmetric, and also satisfies the new secant equation. Okay, so this will define a particular BK plus 1. Now what have I not specified in this optimization? I haven't told you what this norm is. So each choice of norm gives a different result, a different BK plus 1, and the only thing I know about that new BK plus 1 is that it will definitely be symmetric and satisfy the secant equation. So each choice of norm gives a different BK plus 1 satisfying the important secant equation, and thus a different choice of norm specifies a different quasi-Newton method. But nevertheless, a different quasi-Newton method in this spirit, one that's derived by asking to match curvature, by asking to match slope at two subsequent points of the iteration. Okay, so this actually has a solution for a particular norm, and developed in this way, it actually has a different name. It's a slightly different than BFGS, but it's useful. This development has been useful for us to explain what BFGS is. The observation for BFGS says that, okay, well, suppose that I solve this optimization problem, and let's even suppose it's easy to solve. That still leaves me with an approximation to the Hessian. So what were the two key points that we needed? Let's flip back a few slides just to make sure that we understand what we need. Remember, we need, so we've been talking about point B so far. This is what led us to that optimization problem. But on the other hand, how about this? We also want this computation to be easy. And what's hard about this computation? Well, in particular, it's this inverse that I'm concerned about. So the idea of BFGS is, instead of coming up with an iteration that goes from one approximation to the Hessian to our next approximation to the Hessian, what if we could come up with a simple iteration that goes from one approximation of the inverse Hessian to the next approximation of the inverse Hessian? Maybe I could just completely avoid any kind of inversion. So this is exactly the idea of BFGS. Now, I just want to add one small point, which is that I don't want to imply that actually that for this choice of BK that I outlined, inverting it is difficult. In fact, it has a lot of special structure, and you can use something called the matrix inversion lemma to invert it without too much trouble. But nevertheless, this is the key idea of BFGS. In particular, BFGS says, let's write HK to be our approximation of the inverse Hessian. So let's write HK to be BK inverse. Then what are the three requirements that this optimization problem is effectively saying? Requirement 1 is that BK plus 1 is close to bk. That's what the objective tells us. 2 is saying that bk plus 1 is symmetric. And requirement 3, the secant equation, is just saying that bk plus 1 satisfies the secant equation. But you can see that I can actually accomplish all of this while staying in the space of hk instead. So let me write out these 3 requirements. bk plus 1 is close to bk is not the identical relationship, but extremely related to asking that hk plus 1 is close to hk. In other words, I'm going to build an optimization problem that instead of b minus bk is going to minimize h minus hk. Similarly, b is symmetric if and only if its inverse is symmetric. So I can ask that hk plus 1 is symmetric. And finally, the all-important, or in any case, defining aspect of what we've done so far, the secant equation, you can see that I can equally well express it with hk instead of bk. So hk plus 1 satisfies the secant equation. What does that look like? Well, if the secant equation for b is that bk plus 1 sk equals yk, the secant equation for h is just taking the inverse. So it's sk equals hk plus 1 yk. In other words, instead of bsk equals yk, it's sk equals b inverse yk. So since I have these 3 things, I can directly write down the analog of this optimization problem, but now for hk. So my hk plus 1 is going to be the argmin of the optimization problem, h minus hk, subject to the 2 points that we said, symmetry and satisfying the secant equation, but the secant equation now expressed in terms of h. H is equal to h transpose, and h yk is equal to sk. Okay, so now that we're focusing on hk plus 1 and iteratively updating hk, it's time to talk about the choice of norm, and that will allow us to get to the specific expression for what hk is. So the norm, again, you're welcome to choose any norm you like, and then if you solve this optimization problem, you have a quasi-Newton method. BFGS specifically uses a weighted Frobenius norm. So let me remind you what this is. If I have a matrix A, the Frobenius norm of A is really an analog of the L2 norm of a vector. So in other words, it's just the sum over all the elements of A squared. The same way that the Euclidean norm squared of a vector is just x1 squared plus x2 squared plus x3 squared and so on. The weighted Frobenius norm, okay, this is called the Frobenius norm. The weighted Frobenius norm, sometimes denoted by a W, with respect to a particular matrix that's positive definite W, is equal to the Frobenius norm of square root of W. Again, W is positive definite, and as we've discussed in previous lectures, a positive definite matrix always is going to have a square root, times A times W, the Frobenius norm of that. So this is called a weighted Frobenius norm. If we choose a particular choice of W, which I'll write down in a minute, it turns out that hk plus 1 has a very simple iterative solution that updates it from HK. It's very inexpensive to obtain HK plus 1 once you have HK, and so on. So we're going to choose BFGS uses W equal to an average Hessian. The integral from 0 to 1 of the Hessian of f at xk plus t a to k dk dt. So now you're saying, wait a second, I need to compute this Frobenius norm weighted by a vector w that requires me to compute the Hessian, which is what we're trying to avoid in the first place. But that is actually just for the analysis and for the formal definition of the algorithm. It turns out that if you use this w, then we never need to actually compute it, because with this choice of w, with the choice of norm, this weighted Frobenius norm, hk plus 1 has a very simple solution. So then hk plus 1 is equal to identity minus, I'll define rho k, we haven't defined that yet. Sk and yk are what define the secant equation. Remember, sk is xk plus 1 minus xk. Yk is gradient of f of xk plus 1 minus gradient of f of xk. Times hk times that matrix again. This is intentional, this flip. This is sk yk and yk sk. It's because they're transposes of each other. Plus rho k times sk transpose. You know everything in this equation. You know what hk is, you know what sk and yk are, and rho k is just a constant. It's equal to 1 divided by yk transpose sk. Okay, so what this tells us is that in order to, we can obtain hk plus 1 from hk just using this equation. And multiplying this out, you'll see that hk plus 1 differs from hk by just a rank 2 update. And I'll leave it for you to check, it's just a simple calculation, that indeed hk plus 1 satisfies the secant equation. So just plug in yk and make sure that what comes out is sk. Okay, so now we've said so far how to get hk plus 1 from hk. So we're ready to give the BFGS update, and we'll only need one other thing, which is to say how do we choose a step size. So I've promised you that we're going to come back and talk about the specific flavor of backtracking line search. But except for that, we're now in place to give the BFGS algorithm. So for k equals 1 up until t, some number of iterations that you want to compute, or until a particular termination criterion is achieved. So one common one is that the gradient becomes small enough. We compute. We do. First, we compute the update direction. dk is equal to minus, so what goes here? It's the inverse of our approximation of the Hessian. That would be, for example, bk inverse. But we don't have to do that because we've directly been working in the inverse space already. So this is just minus hk times the gradient of f of xk. Now with dk in place, we can update xk plus 1 is equal to xk plus a to k dk. A to k is going to be chosen by backtracking line search, or just writing this out, this is equal to xk minus eta k hk gradient of f of xk. And eta k is chosen from a backtracking line search. And once we have xk plus 1, now we can update sk. sk is equal to xk plus 1 minus xk. And we can also update yk. yk is equal to the gradient of f of xk plus 1 minus the gradient of f of xk. And once we have sk and yk, let me just flip back one slide. Once we have sk, yk, and we already knew hk from the previous iteration, that's enough for us to update hk plus 1 using this simple recursion here. So we can compute hk plus 1 equals, I won't copy it out, I'll just write from previous slide. And that is the BFGS algorithm. So let's briefly talk about backtracking line search. So we've talked about backtracking line search before. When we talked about it in the context of Newton's method, the backtracking line search we introduced, and this is a common one, just required that you take a step that sufficiently decreases the function. So we have a sufficient decrease condition, which says that f of xk plus eta k dk, you have your direction. Again, don't be confused by the lack of a minus sign. dk has that built in. Should be less than or equal to f of xk plus some constant times eta k gradient of f of xk dk. You may want to look back to our lecture on Newton's method when we introduced backtracking line search and discussed it a little bit more in depth. So now we're going to impose a second condition. We will also require a second condition that essentially is saying that you don't want to take a step and be somewhere where things are even steeper. Because if things are even steeper, then maybe you should have gone a little bit further. Ideally, you'll take a step to a place where things are not as steep. And basically, this second condition, which says what I mentioned, can be written as gradient of f of xk plus eta k dk. So note, this is a condition on the gradient. It's not a condition on the function. In the direction that we're going, so it's saying the gradient in the direction, the steepness in the direction that we're going is greater than alpha 2, some other constant, times the gradient of f of xk dk, where alpha 1 and alpha 2 are between 0 and 1. So this now fully specifies our computation for the algorithm for BFGS. One final word that I want to mention about BFGS is about the setting where perhaps even BFGS is too expensive for our computational appetite. So the computation required, as I've written it, for BFGS is basically now quadratic in the dimension instead of cubic, because we avoid this computation of an inverse. But on the other hand, nevertheless, HK is maybe an n by n dense matrix that we're keeping around. Requires a lot of memory, and taking the product is expensive and squared. If you think about gradient descent, in some way, it's what we're aiming for in terms of memory requirement or in terms of computation time. It doesn't have any n squared. We don't have to keep n squared around in memory or anything like that. So the idea behind limited memory BFGS is to say, let's look back at how HK is formed. So the observation is that HK plus 1 is a rank 2 update from HK, and in particular, all you need to derive HK plus 1 from HK is two vectors, SK and YK. Let me flip back again just so we can, for 1 minute, look at the update for HK to HK plus 1 so we can see that explicitly. So looking here at the update, we see that as long as I know SK and YK, that means that I can compute HK plus 1 from HK. So the idea here is, what if I just keep some number of these, but not all of them? Again, what does that mean, and what implications does it have? We should really think about n as being huge. So if n is some very large number, HK is a very large number, then storing HK plus 1 explicitly requires n squared calculation. But storing, let's say, 100 pairs of SK and YK just requires 200 times n. If n is much, much bigger than 200, I would much rather have storage 200 times n than n times n. So this is the idea. If you think about n being truly astronomical, then 200 times n is essentially n if we compare it to n squared. So limited memory BFGS is exactly saying, let's just keep the SKs and YKs in a particular window and start forgetting them. The details of LBFGS, L for limited memory, are exactly about how to implement this in an efficient way. And we're not going to talk about all of those details here. Instead, I'll refer you to the Nassadal and Wright book. But limited memory BFGS, or LBFGS, is something that also has been extremely influential and important, especially for large-scale optimization problems. And machine learning, which has been a big motivation for everything we've done in this course, is one of the key areas where we get structured large-scale optimization problems, and therefore an area where LBFGS has been used and has had impact. We're going to end this lecture here.